Hi, welcome to today's session. Today we'll be looking at Organic Chemistry 2. In our session today, we'll be taking a look at how to describe alkanols and alkanoic acids. We will be able to explain some organic reactions and then answer exam-style questions on Organic Chemistry 2. All right. From the Organic Chemistry 1, you were taught saturated and unsaturated hydrocarbon. So can you take a look at this structure and determine if it is saturated or unsaturated? Okay, if you pick saturated, green, you are correct. If you pick unsaturated, that is a red, there may be need for you to check our earlier video on Organic Chemistry 1. First of all, we are going to look at alkanols, or using their general name, alcohols. So alcohols are a family of organic compounds that contain carbon, hydrogen, and oxygen atoms. Mind you, they are not hydrocarbons. Remember, in our Organic Chemistry 1, we said hydrocarbons are compounds that contain only hydrogen and carbon. This carbon and hydrogen only. So alcohols, alkanols, alkanoids, and some other organic compounds are not hydrocarbons. So hydrocarbons are limited to alkanes, alkenes, alkynes, and some other cyclic hydrocarbons, and also some aromatic hydrocarbons, meaning that these ones have only carbon and hydrogen only. Any other substance that have more than that can still be seen as an organic compound, but not hydrocarbon. So the functional group of an alcohol is the OH. Remember, we said the functional group is what is responsible for their chemical behavior. So alcohols are very soluble in water. As a result of this, they are hydroxyl group. For example, we can have the first member. Remember, we talked about NAMI. So NAMI, you can have, if we have it as 1, said MEP B, and polygons. MEP and polygons. So since it's just one carbon that I have, I know it should have a met. And since the name ends with nol, so that will be a methanol. So that is the first member, methanol, met. The second member, of course, ethanol from earth. And the third member, see, propan-1-O. Now, it could be a propan-2-O if this OH that you have here is placed here at this second carbon. If it is placed at the second carbon, if you have the OH at the second carbon, if there's an interchange where the OH comes there and the H comes there, then definitely you have a propan-2-O. This is positional isomerism. Positional isomerism. All right, so we want to classify alkanols. Alkanols can be classified based on 2 types. One, we can classify based on the position, of the OH group. Okay, we can classify based on the position of the OH group. Which carbon is it attached to? Are you getting now? Relative to carbon atom. So which carbon is this OH attached to? So if the OH is attached, we first have number 1, we have what we call primary alkanol, or you call it 1-degree alkanol. In this case, the OH is attached to a carbon that has 2 hydrogen. Okay, so basically what we are saying is that we have an R, we have a C, H, H, and no H. So if the OH is attached to a carbon that has 2 hydrogen atoms, okay, we say that is a primary alcohol. That is primary alcohol. An example is ethanol, okay, which is CH3, CH2, OH, right? We can also have a secondary alkanol, okay, which we call 2-degree. In this case, the OH is attached to a carbon with just 1 hydrogen atom. Okay, so basically what we are saying is that we're having R, C, and R, only 1 hydrogen atom, that's the position, and then OH. So in this case, we say we are having a secondary alkanol. Of course, we could have a case study like this, CH3, and the CH3, and that's CH3, there's an H, and this is OH. Okay, so if I have this, this is a basic tertiary alcohol. No. All right. So I could also have a third one, which we call tertiary, tertiary, or you say 3rd degree. Okay. This one happens when the OH is attached to a carbon that has no hydrogen atom. So basically, I'm having an alkyl group H, an alkyl group, another alkyl group, and then OH. So when I have this scenario where I could have a CH3, see, it could be more than CH3, these are just for illustration. So when you have these examples, then you said these are primary alcohol, remember, attached to a carbon atom that has 2 hydrogen. Secondary, attached to a carbon that has only 1 hydrogen, only 1. This one attached to a carbon that has no hydrogen. Another way we could classify alkanol is based on number of OH group that is present. Number of OH group that is present. So in that case, I could have a first one called monohydric. Monohydric. Okay. Some also call it monohydroxyl. That is fine. Monohydric. So basically, we are saying that I'm having just 1 hydroxyl group attached. So this monohydric is still an example for ethanol. Okay. And likewise, I could have for dihydric, or like I said, it can also be seen as dihydroxyl. So in dihydric, you have a case where you're having 2 hydroxyl group. Okay. So I'm having hydrogen here, hydrogen here, hydrogen here, hydrogen here. To name this, I will name this, count the number of carbon, remember 1, 2. So 2, there should be an eth. So this is ethane 1, 2, 1, 2, diol. Diol. So since it's dihydric, the name will not just be a norm, it's going to be a diol, dihydric. Then we could also have the last one, which is trihydric. Okay. And in this case, we are saying that there are three OH group, three OH group. So I also have another OH group. Okay. Because you have your hydrogen, you have your hydrogen, and your hydrogen. Okay. To name this, count the number of carbon again. 1, 2, 3. That is the longest carbon. So you should have a prop. So this is propane, 1, 2, 3, triol. So we can classify alkanols, number one, based on the carbon atom that the hydroxyl is attached to, where you can have primary if it is attached to a carbon with 2 hydrogen atoms. You can have secondary if it is attached to a carbon with 1 hydrogen atom, and you could have tertiary if it is attached to a carbon that does not have a hydrogen atom. I mean the carbon that it is attached to. Why the second scenario, we could have based on the number of hydroxyl group that is present. So I have OH, only one OH, that is monohydric. If I have 2 OH, that is dihydric. And in naming, the name will also reflect that 1, 2 diol. Why in the case of 3 is trihydric, and the name will also reflect that as 1, 2, 3 triol. Okay. Now, carboxylic acids contain a functional group of carbon, hydrogen, and oxygen atom, basically saying that this one too is not hydrocarbon, it's an organic compound. So the functional group is written this way. You can also write it as COH. For example, that is methanoic acid. If it is 1 carbon, meth, remember meth, so methanoic acid. This is also called formic acid. We also have ethanoic acid. Okay, you can also call that vinegar. So what do you think the carboxylic acid with 3 carbon atom is called? So it is called propanoic acid, which can also be written as CH3, CH2, CH. If you get that correctly, you can give yourself an applause. All right. We now want to look at some organic reactions as a result of these functional groups. The first one we'll be looking at is esterification. Esterification is a reversible reaction between alkanoic acid and alkanols to form esters, or you call them alkanoates. So basically, we can represent that in a general form, saying that RCOOH reacts, okay, reversibly with an ROOH to give us RCOO. Okay, let me put a prime here just to differentiate between the R so that you know which one we have here. Okay, plus water. So basically, you're having an acid, ethanoic acid, or any alkanoic acid at all, reacting with an alkanol to form an ester. You call this ester or alkanoids. These are esters or alkanoids. And now in naming them, it's different. You name by splitting into 2. I'll split into 2. I will name the first one as an alkyl group, while I will name the second one as an alkanoid. So you can see here I have the 2 carbon alkyl, that is ethyl, and I also have 2 carbon on the other side, ethanoate. If you were to be 1 carbon, like in this case, if you were to be 1 carbon here, just 1 carbon, you can see that, oh, this is CH3. Let's quickly correct that. This is CH3. All right. So if you have only 1 carbon, then definitely that is methyl ethanoate. If it were to be just one carbon that is in the alkanoate part here, it's going to be methyl methanoate. If I have only one carbon. So the number of carbon you have in the corresponding side determines the naming of an alkanoate. So sometimes you may be asked, how do I know what formed these two? Just break it off and add your OH back here. You know, you have an alkanol. Add your H back here, then you have an alkanoate. So basically, we could have a model in this form, okay, where the OH and H combines together to form an element of water. Other aspect of organic reactions we'll look at is substitution reaction. Substitution reaction takes place with saturated compounds, that is an alkane. So basically, since it is saturated, let's pick an alkane. Since it is saturated, please maintain. Since it is saturated, there is no way it could take any other electron. We know that carbon is tetravalent in nature. So there is no way it could take any other electron. So as a result of this, it could only undergo substitution reaction. All alkanes can only undergo substitution reaction and in the presence of sunlight. Now, if I have this case, I can now react this one, let's say, with halogen, okay, chlorine, for instance, it's called chlorination. What I'm going to have is this will only be substituted. Remember, in a football team, if you have 11 players that need to play, if I'm going to bring in another new player, I must substitute. So one of these hydrogen has been substituted, okay, with an element of chlorine, such a way that the substituted hydrogen will now react with the other atom of chlorine that we have. So when I have this case, this is substitution reaction. And this particular is called chloromethane. It's chloromethane. One carbon, you remember? So chloromethane. This reaction can continue. Take for instance, I could have the CH3, Cl, which is another formula for this. Okay, that is a condensed formula, plus Cl2 again. Then the substitution will continue such a way that I only have CH2, Cl2 plus ACl. If I continue that again, the CH2, Cl2 can be further substituted where we have CH, Cl3, okay, plus ACl. Because this particular reaction is important, this is called chloroform, which is an anesthetic used in the health sector. All right, we could also continue this reaction until everything is substituted. The chloroform itself could be substituted such a way that I'm having CH, Cl3 plus Cl2, and then I'm going to have CCl4 plus ACl. So this is complete substitution reaction, and this is called tetrachloromethane or carbon 4 tetrachloride. Tetrachloromethane, tetrachloromethane, or you call it carbon 4 tetrachloride or carbon tetrachloride. So when you have this kind of reaction, we say this is substitution reaction. The hydrogen atom is being replaced. It's not added to it, it's just substituting. And only saturated compounds, hydrocarbons, that will undergo this. Except for benzene, though unsaturated can undergo substitution reaction as well as addition reaction. Now, in the case of addition reaction, in this case, this is characterized by unsaturated compounds. Unsaturated compounds, and which are alkenes and alkynes. In this case, we will add a substance to them. It can be hydrogen. You can just hydrogenate. Take, for instance, I have this. This is an alkene. All right, plus hydrogen. Okay, so I'm going to have the double bond we have to give way to make it saturated now. It was initially unsaturated, now it is saturated. When this happens, you have addition reaction. One notable thing about addition reaction is the fact that only one substance will be formed. There is no any other thing that will be formed. Only one will be formed. Okay, so this is addition reaction. It could also be C2H4 plus chlorine. Okay, I will still get the same thing. I could have C2H4 Cl2. Basically, in structure, I'm having something like this: a chlorine, a hydrogen, could also have a chlorine here, a hydrogen, and I could also have it at this point. I could have it here and here. They still mean the same thing. So addition, you are adding something. It could also happen for alkenes, but in the case of alkenes, only one double bond will go. I mean, for alkynes, with a triple bond, only one of the double bond will go, except for continuous addition. So if I add just hydrogen to this, okay, I will form an alkene with just a double bond. Okay, with just a double bond. If I now add another hydrogen, then it becomes saturated. I will just form only this. Take the bond as hydrogen. So when you have this case, that is addition reaction. Now, all hydrocarbons born in air oxygen to form carbon dioxide and water. So basically, we are saying that this is the general equation. So if I have, for instance, I have CH4 plus, and I have O2, okay, automatically I know it must give me carbon dioxide plus water. But how do I balance it? Simply, here, if I look at this formula and I look at this equation that I'm having, x is equals to 1 and y is equals to 4. You know, it corresponds to this. X means there is nothing after C, so that means only 1. And after H, I have Y, so only 4. So that's how I could get that. So I know that automatically here must be X. And since X is 1, so here is 1. I don't need to put anything. But what would I put for in the front of O2? That would be 1 plus 4 over 4. Okay, don't do the mistake of adding 1 plus 4. It's rather 1 plus 4 over 4. So that is what? 1 plus 1. And that will give us 2. So I'm having 2O2. Okay. For H, what do I do? Y over 2. So let's do Y over 2. Y is 4. So 4 over 2. So here I will just put. Now I already have a balanced equation. That is balanced. If I have situation where I have something like C2, okay, and H6, what do? I say plus O2. Okay, look at this one. It's important. I still have my CO2 and plus water. So if I'm to balance this, what do? I will still write that my X is equals to 1 and my Y, my X is equals to 2 and my Y is equals to 6. So automatically, since this place is X, so I can have 2 here. Now, I must do the same thing by saying that X is 2 plus 6 over 4. Now, in this case, you can see I have a fraction, and that's why I'm doing that. So that means 2 plus 3 over 2. So I must find the mathematics of this 2, okay, so such that I have 4, okay, plus 3. So that is 7 over 2. So I will write that. So that is 7 over 2 here. And y here is going to be 6 over 2, which is 3. Okay, y over 2, and since our y is 6, so that will be 3. I can leave it this way, but if I don't want it as a fraction, all I need to do is to multiply through by 2. If I multiply through by 2, it will cancel out this. Then I could have 2c2 h6, okay, plus 7o2, and that will give us 4co2 plus 6h2. So that is if I don't want to leave it in fractional form. So for every hydrocarbon discombustion reaction, you can use the general formula to write the equation. All right, hydrogenation is simply hardening of oil. Now, oil, if I have oil, okay, plus hydrogen, then I could have what you call margarine. So that is what hydrogenation is mainly for in organic compounds. Now we know that oil is liquid form. So the fatty acids in oil that we're talking about now is the one that is unsaturated. So that is why you see that oil will always be in liquid form, because it's unsaturated. The moment hydrogen is added to it, it is unsaturated. The moment hydrogen is added to it, it becomes saturated. And that is why it becomes solidified, saturated. And that's why every good oil is unsaturated. Even if cold season, dry season, it remains in its liquid state. Another chemical reaction is samponification. Samponification is the alkaline hydrolysis of fatty acids. It is the reaction between a fatty acid and an alkali to form soap and glycerol. So basically, if I have this, I could have it as a form of general equation where I'm having R, COO, R, I have another COO, R, I have another COO, R. Okay, I could have other R added here too. Okay, now if I have this plus 3 molecules of a base, majorly maybe caustic soda, then I could form what we call soap, which is basically the sodium replacing the R part, as I have 3 molecules of it, replacing the R side, and to now form glycerol. Glycerol is simply propane 1,2,3-triol that I've given to you earlier on. Okay, so when you have that, then you said samponification to form soap. So the reaction that leads to the formation of soap is called samponification. Another reaction we may want to look at is fermentation. Fermentation occurs when a glucose-containing substance, or let me say carbohydrate, I don't want to use the word glucose, carbohydrate, okay, is broken down to form ethanol and carbon dioxide. And this is the reason, and let me ask this question. If I have a palm wine in a bottle, a freshly prepared palm wine in a bottle, why is it that I must not fill it to the brim? It is as a result of this reaction. Because if I fill it to the brim and allow it to stand for a while, the glass will shatter. The glass will shatter due to the production of carbon dioxide. So if it is filled to the brim, the pressure generated by the gas, if there is no space to contain it, then it will make the glass to shatter. So most often when you see your soft drinks or some other drinks that they were not filled to the brim, it is not a way to cheat you out of your money. It is basically to make allowance for the gas or the carbon dioxide that is present in it, especially for wines or other carbohydrate containing compounds, grapes, palm wine, or that will have glucose in them. Another one we want to look at is polymerization. Polymers are very large molecules made when hundreds of monomers join together to form a very long chain. So, polymerization is the reaction that we use to convert monomer into polymer. And this is as a result of covalent bonds between atoms. So plastics are synthetic polymers that can be shaped by heat or pressure. We also have what we call thermosets. These thermosets, you can't shape them. Once you make them, they remain like that. But plastics, they can be shaped by heat and pressure. Call them thermoplastics, thermosets. Thermosets, you cannot shape them. But thermoplastics, you can shape them. We can look at polymerization in form of addition polymerization. This is a notable addition polymerization where I have about 4 monomers added together plus this monomer. One of the monomer is 18. So when they react together, then they form what we call a polymer. This is a polymer. All right. So I can use N to put there if I don't know the number, because it's going to be a very large molecule. But because here we just have only 4. 1, 2, 3, 4. So I could form this 4. But this is called repeating unit. This one part is called what? Repeating unit. And this is indicated this green. So 1, 2, another 1, 2, another 1, 2, another 1, 2, another 1. So this is 5 monomers joined together. Another thing that is notable is that the double bond here will disappear. There will no longer be any double bond. There will be a single bond. So we have 18, then we are going to have polythene, your polythene bag, or polyethylene bag. Another example that we could have for polypropylene, okay, I put a C here. This is the repeating unit for this. Another repeating unit, all right. I can just put an N. So this is propene, which is a monomer, okay, which is a monomer. Then I could have polypropene. In all of these cases, this is addition polymerization. Only one single thing is formed. I can also have polyvinyl chloride, where this is just a vinyl, okay, vinyl chloride, a single one. But if I have more of it, I could form a polyvinyl chloride with this repeating unit called PVC. Another polymerization we can talk about is condensation polymerization. Now, in this case, there is 2 different monomers. In the last one we did, we have the same type of monomer addition. But in this one, 2 different monomers. Okay, this is one monomer, this is another monomer. This monomer has a functional group ROCOOH. This monomer has a functional group ROH. Okay, so this, the H from the OH part and the OH are condensed together, and that's why there will be elimination of water molecule. There's elimination of small molecules. In condensation polymerization, there will be elimination of small molecules. And here, the bond that is formed, C double bond O. This O is from the alcohol, okay, while the C double bond O is from the carboxylic acid that we have. And we could, if I have two molecules of it, this is the repeating unit, the one in bracket is the repeating unit, okay, and you can see this is the linkage that we have. This is a typical example of a polyester. This a polyester, since this is a form of esterification reaction. So we have polyester. Another example we could have is polyamide, as we can see in proteins, where you have two different functional groups, a COH functional group, and a amine functional group, okay, will react together. And you could see that here, only the double bond from the carboxylic and the NH. So basically, one hydrogen has been abstracted, okay, and the OH here has been abstracted to form water. So from here, I have OH, and from here, I have H to form water molecule. And then you now have what we call the peptide linkage or the peptide bond, okay? And this is a notable example of polyamide, a polyamide. Okay, so poly means large molecules. All right, so let's try and solve some questions. Question number 1 said 2-methyl-butanol is an example of what? So I want to know if it's an example of dihydric, tertiary, secondary. Now, the first thing we must do in order to answer this question is to draw the structure. So butan, the name is butan. That is where the real name is from. So a but must have 4 carbon. 2, 1, 2, 3, 4. And I know that is a 2-or. So if it's a 2-or, I must have OH at carbon 2. And there's also an attachment, 2-methyl. So I must also have a CH3 at carbon 2. So look at this. Hydrogen, 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 hydrogen. So if I look at this, all I will ask myself, remember, we said for primary, it must be ROCH2OH. For secondary, it must be ROCHOH. For tertiary, it must be ROCOH. So let's look at this. This is an R. The carbon does not have any hydrogen at all. That's what we are just basically saying. It's under R, and the 2 is under R. So this suits into our tertiary. Okay, so basically this is tertiary. Remember, dihydric means having 2 OH. It's having, and this does not have 2 OH. So it could be dihydric. And it cannot be secondary because it does not have 1 hydrogen. It cannot be a primary because it doesn't have 2 hydrogen. The arachidonic acid found in human sweat. Okay, these are all arachidonic acid, and they're asking us the one found in human sweat is what? So let's basically use this one. This one is the one found in vinegar. Okay, this is the one that you find in ant or bee. When a bee stings someone, you have formic, or you say what? Metanoic. Metanoic acid. So this is the one you can find in sweat. This is just a methyl group. not an alkanoic acid. The reaction between ammonia and ethyl ethanoate produces, okay, so let's look at ethyl ethanoate. Ethyl ethanoate can be hydrolyzed. Ethanoate is CH3COO, that's an ethanoate, and then ethyl, that will be C2H5. We can hydrolyze this. I've told you that earlier. So if I'm going to break this, I know that I must form, because this is formed from ethanol and ethanoic acid. So the ethanol must first find itself, while the ammonia, a part of it, the NH2, will be attracted to this. So that such a way that I will have CH3, COO, NH2, and amide plus C2H5OH. So if I have this, basically, that is, I'm getting ethanol and ethanamide. Ethanol and ethanamide. This is an ethanamide. Ethene is prepared industrially by what? This is a way to remind us of some of the other reactions we have learned. We know that reforming is basically improving what? The quality of petrol. To improve the what? The anti-knocking properties. To ensure that petrol doesn't knock engine. That is reforming. Polymerization is when you add, take for instance, if you polymerize ethene, you get a benzene. So ethene cannot be prepared by polymerization, since ethene is a monomer on its own, and neither by distillation, so by cracking. Cracking is quantity, to increase the quantity of petrol by breaking a heavier hydrocarbon into a lighter hydrocarbon. And most of the product of cracking, when you crack, basically you crack an alkane. You crack an alkane, and most of our results are smaller alkanes plus alkenes. And this is the way most alkanes are being prepared. Question 5. In the process below, P and Q respectively represent what? All right. You can see a mono, and a poly. Poly can only be as a result of, okay, monosaccharide and polysaccharide. Okay. In this case, we know that we are talking about carbohydrates, where I have two molecules being joined together. So if I break down these substances, then I'm going to have, I call that hydrolysis, breaking down. In the other one, you may want to say, okay, if I'm getting this, would I be condensation or would I go for polymerization? Polymerization is the general name for this. So when I'm going, I polymerize. And when I'm breaking down, that is hydrolysis, to break down. So polymerization and then hydrolysis. Ethanol is soluble in water due to the presence of what? Okay. Mostly, the solubility of ethanol is as a result of its hydrogen bond. It's as a result of its hydrogen bond. This hydroxy group has what we call hydrogen bond in it. And as a result of that, it will be very, very soluble in water. The hydroxy group is what makes it soluble in water. The compounds, this and this, can be distinguished from each other using what? All right, let's look at, we know that ammonia can be used for hydrolysis, Now let's look at what do we have here and what do we have here. The first substance that we have is basically alkana, while the second substance that we have is alkanon, which is a ketone. So how do we distinguish between these two? We must understand what we call functional group testing. How do we test for alkana? There are many tests that can be done for alkana. We could have the Ferlin solution test, where you have a brick red precipitate. We could also have the Toulouse reagent, where you have a silver mirror, okay, on the side of the tube. All right. But for alkanon, when you want to test for alkanon, most often what you just check for is to see if there is carbonyl group present in it, using 2,4-dinitrophenylhydrazine, using 2,4-dinitrophenylhydrazine. But in this case, there is not 2,4-dinitrophenylhydrazine here. So basically, we are left with only one option, which is Toulouse reagent. Benedict solution, yes, you may want to say, okay, what of Benedict solution, which is a test for reducing sugar. Okay. But in this case, we are not even talking about reducing sugar. This is not a polymer. It's just a simple alkana. This is simple propanal. So it's not even a polymer at all. So we'll not be talking about reducing sugar. We'll be talking about test for alkana functional group, which is using a Toulouse reagent, where you have what? Or you call it silver mirror test. So it will be positive. You have a silver mirror with alkana, and there will not be any change with alkana. Most often, you can also be asked to differentiate between alkana and alkanoic acid. If I have alkanoic acid, of course, because of its functional group RCOH, this one I could use a bicarbonate to test for it, knowing that there will be effervescence and I'm going to have a liberation of CO2 to differentiate between them. Which of the following types of alkanones undergo oxidation to produce alkanoic acids? Now we have been able to classify alkanones into primary, secondary, and tertiary. But now we want to look at how do we differentiate between them. Primary alkanones, due to the presence of their what we call nascent hydrogen in them, you can oxidize them initially, to propanals. Okay, you can to alkanals, and then in complete oxidation, they'll be oxidized to alkanoic acid. That is incomplete. If it is incomplete, alkanol will be oxidized to alkanals. Are you getting now? Why complete oxidation to alkanoic acid? What I'm saying is that if I have C2, if I have ethanol, let's use the name, it will be oxidized to ethanol, and that will be oxidized to what? Ethanoic acid. That is for primary alkanol. For secondary, however, if I have the RCHOH, this can only be oxidized to alkanones. This can be oxidized to alkanones. So if I have a secondary alkanol, okay, I'm going to oxidize it to alkanones. While for tertiary alkanol, okay, this cannot undergo oxidation. So if I oxidize it, there will be no reaction. There is no any nascent hydrogen present for a reaction to take place. So in this case, only primary alkanol can produce alkanoic acid. That is one only. And that will only happen when you have complete oxidation, not incomplete oxidation. When you have complete oxidation. Now, in this question, we asked for the purpose of the H plus in the reaction. Sometimes hydrolysis can be acidified, and the purpose of this acidified hydrolysis is majorly to act as a catalyst. So in this case, when I hydrolyze ethyl ethanoate to produce its constituent, which is ethanoic acid and ethanol, okay, what it's just doing, since it's acting as a catalyst, is what? To increase the rate of hydrolysis. Increase the rate, since majorly what catalyst does is to increase the rate of reaction. And since this reaction is hydrolysis, so I will not be going to increase yield of product. No, I will basically be looking at it from the position of it will increase the rate of reaction. And this reaction is called hydrolysis. And this question said the decarbonylation of ethanoic acid will produce carbon dioxide and what? So if I have this, basically all I need to do is to write out the formula. They say it has been decarbonylation is another example whereby carbonyl or carbonyl is being removed. Now you now have CO2. So the CO2, the carbonyl that you have here has been removed. So what do you have left? So basically all we have left is CH4. Just simple adding your CH3 and then the hydrogen. Since it is decarbonylation, then you have methane left. Since it's only one carbon, and then that is methane. So thank you so much for coming to today's session. In another session, we are going to be looking at other aspects of chemistry. Thank you.